In the textbook, we find symbols for these three special Boolean functions. Alternative symbols are also used. For the AND function, we use multiplication sign. For the OR Boolean function, we use the addition sign. And for the NOT operation, we simply use the apostrophe. The textbook uses these symbols, but I will also be using these alternative symbols in our lecture. So just to give you an example on how we use these symbols, so if I say 1 times 1, this really means 1 and 1. And the output here is 1. So if we do 1 and 0, this is 0. 0 and 1, that's 0. And 0 and 0, that's 0. As you can see, for the logical gate AND, the multiplication sign works pretty well. It looks like we're doing just our regular arithmetic with real numbers. Now let's check the OR function. If we do 1 plus 1, this really means 1 or 1, and that is 1. Now this doesn't work very well with our regular algebra. 1 plus 1 is not 1 in our regular arithmetic. But remember, this is not our regular arithmetic. This is a Boolean function, and these elements are not really real numbers. These are true or false or on and off, and we use zeros and ones. Now, if we do 1 plus 0, this really means 1 or 0. That's 1. 0 or 1, that's 1. And 0 or 0 is 0. So it works pretty well, except for this first case where 1 or 1 is 1. Now in the textbook, we also see some properties of Boolean algebra. And those properties actually define the Boolean algebra. And those can be found in the textbook. I want to just illustrate two of those properties. The distributive property is part C of the theorem. This is C in theorem 10.1. Now I'm using the alternative symbols here. This is very similar to our arithmetic or algebra, regular algebra, when we distribute a number, multiplication into a sum. So x and then in parentheses we have y or z. We can simply distribute x into y plus z. Now there is a second distributive property that is also true, but it's not true for our regular algebra in arithmetic, where we distribute the sum into a multiplication. Here we distribute x plus into y times z, and we get this expression. The properties in theorem 10.1 can actually be proved. For example, this distinctive distributive property where we distribute the addition into a multiplication, which is really the OR function into the AND function, obtaining this expression here. That can be proved by simply comparing the two truth tables. So because we have 3 variables, then there are a total of 8 inputs. And for each of those 8 inputs, we have an output that can be calculated. For example, if x is 0, y is 0, and z is 0, then we substitute those values in this first expression, and we obtain 0. And we substitute those values into the second expression, we also obtain 0. And if we do that for every single case here, every one of those 8 cases, and if we get the same answers, the same values in both truth tables, then the first expression is the same as the second expression. And that's a way to prove that this expression is equal to the second expression. Let's take a look at this property, idempotent property. It's actually really easy to prove because this expression or this equation here has only one variable, then we can simply split that into 2 cases, right? Case number 1, suppose x is 0. If x is 0, then we would have 0 plus 0 equals to 0. And that is true. So this is okay. In case number 2, suppose x is 1, then we will have 1 or 1 equals 1. And that's true. So that proves that x or x is x.